Okay, so we had the exam one the other day, right? There was multiple issues went down with the exam. There's some problems that, like, if you entered in the right answer, it still wouldn't accept it. And so they're dealing with that. And hell, there we go. Some people, like, halfway through the test, you just like erase all their answers, like an email. So after school today, I'll be meeting with the course coordinators. They're going to figure out how to resolve these issues. I don't know what they're going to do. They might just mark the problems that had issues. They might just mark those as correct for everyone. For the people who that just deleted all their answers, I'm not sure what they're going to do about that. I think one of the main reasons why they have the retest isn't just so that y'all can just get a better grade. One of the reasons why they have the retest is because technology fails. So you might have to just resort to the retest and we can work out the issues there. But I'll let y'all know when I find out what the course coordinators and the IT people decide on what needs to be done. All right. So bear with me. All right. We will figure this out. Yes, ma'am. Yeah, the blackboard's wrong. Yeah, you do. Yeah, because this module, let's see, let's go back. Dang it. Yeah, this module, 11, there's 8.3 homework and 8.4 homework. So yeah, there are two homework assignments here for this module. Okay? Not sure why Blackboard is incorrect. So yeah, there are two homework here. And there's also a practice writing assignment. So I guess three homework here. Okay? So let's do some math here. Where were we? Last time we did this problem, I want to bring it back up again. So remember, for this polar coordinate stuff, the four things you need to know, or the first four things we learned, r squared is x squared plus y squared. And you know cosine is x over r, or you could write this x is r cosine theta, y is r sine theta. And sometimes you might want to use tangent theta. So these four definitions we can use. So they say just convert it to rectangular. So if you just mindlessly plug in and substitute, r would be x squared plus y squared. Secant is, what is it? Secant is the reciprocal of cosine. Cosine is x over r. So this would be r over x, right? Taken as r over x. Doesn't look right though. Yeah, but r is the square root of x squared plus y squared. So if you just plug in your substitution, you get this equation, right? And that's legit. But notice how they've written this in the form where r equals, right? We're used to like saying y equals some function of x, right? Not all equations can be written as a function, right? Sometimes you can't get the y by itself, right? Well, here they've written it where r is by itself, right? So they're saying r is a function of theta. In this particular equation, you can write it as a function, right? So when we substitute, this is an equation, but it's not really y equals stuff with x's in it. If we tried to do that, we could try, if we divide both sides by this thing and multiply both sides by x, we saw this is equivalent to x equals 2, right? This is a lot prettier than that, right? But they are logically equivalent, okay? So all they did was say convert it to rectangular. So technically this is correct, right? This is prettier. Sometimes you might want to rearrange these things before you substitute, okay? Or maybe you might use trig identities first to simplify it, right? Before you use these. So keep that in mind. Look at another example. So this one, there's some things that y'all haven't been taught yet. I mean, y'all know what a parabola looks like, right? And you know what the equation for a parabola looks like, right? Right? Most of y'all might recognize the equation for a circle. Like if you had like x squared plus y squared equals 9, you know that's a circle of radius 3, right? Or maybe you might recognize this as a circle of radius 3 that's been moved to the right by 2 units, right? Or um, something like this, let's see, plus 3. This is a circle of radius 3 that's been moved to the right 2 units and move up 3 units, right? Notice if you squared these out though, you would have like x squared minus 4x plus 4, right? So you might have some x terms in there. If you squared that out, you might get some y terms in there. So, right, you'd have to manipulate it to see that, oh, this is a circle, right? If you just have it all multiplied out and stuff, you wouldn't recognize it as a circle, right? Um, And y'all might not know that if you throw a minus in there instead of a plus, that's like an inside out circle, right? That would be like a hyperbola, right? Y'all haven't learned about that stuff yet, or the equations for conical sections and things like that. And these are the things that are typically taught in a pre-calc class at the end of the class. They show you these different equation forms so that you can recognize what the graph of something like this would look like. This class, they kind of go into detail into graphing and polar coordinates. Like in the 12 years I've taught pre-cal, I've never really gone into that in any detail. I focus more on complex numbers, exponentials, and logarithms, right? But in here, we're going to cover some stuff that I'm seeing basically, well, teaching for the first time anyways. So bear with me. Um, so this guy, they have it as r equals, I mean, it's an equation, but it happens to be in functional form. You can actually get r by itself. And the fact that they did that makes me want to look at this equation. Well, that one's not a good example. Y fell out of the equation. The fact that they wrote it as a functional form, that makes me want to, once I do the conversion, it makes me want to write it as y equals a function of x if I can, right? There's no guarantee that I can, but if we just mindlessly do the substitution, r is the square root of x squared plus y squared. And cosine is what? X over r, but r is the square root of x squared plus y squared. There, we're done. Rewrote it as a Cartesian equation. Sure is ugly though, all right? But I mean, we did what they asked. But due to aesthetics, since they wrote this as a function, r is a function of theta, it'd be really cool if I could write this as a function, or at least put it in some form where I can recognize what the graph of it would look like, right? There's not a lot you can actually do with this. If instead of doing this first, what if I rearrange it? Let's say I get rid of the fractions. I'll multiply both sides by this. So now, I mean, I got rid of the fractions. If I multiply this out, I would have r minus 2r cosine theta equals 3. And this I recognize as x. R cosine theta, that's x. This is not a equals, this is minus. There we go. R. So r is square root of x squared plus y squared minus 2. This is just x. Right? That's a little bit better looking than this. I mean, I could have used this and turned it into that, right? But sometimes it pays off to do a little manipulation first before you do the substitution, right? We're looking for r cosine thetas and r sine thetas, right? Or a tangent theta, because that would just be y over x. From here, I might be like, well, what if I did this and then I square both sides just to get rid of the square root? The square roots suck, right? Well, if I squared this out, right, I have x squared plus y squared. If I squared this out and moved the stuff over here, I'd be like, okay, I would have, let's see, I would have a 4x squared. Well, it'd be minus if I moved it over here. And I would have 6 times 2, I would have a minus 12x. And then if I kept the 3 squared on this side, right, so if I took, I could combine these with that. I could probably turn this into a circle. Is the whole point here. This is a circle, right? If I combine the x squared with this thing, and I did, remember completing the square, right? Y'all remember that, completing the square? Where you have like x squared plus 4x, but you really want to write it as x plus 2 squared, right? So let's say this is equal to 0, right? I would take this and I would add 4 to both sides. Right? So if I just had x squared plus 4x equals 0, I'd be like, that sucks. I would add 4 to both sides. Now this is a complete square. So whenever you have these x squareds and the minus 12x, we could add something to both sides and complete the square and make it look like the equation of a circle that's been shifted. Okay. At this point, though, we could turn it into something that looks like a circle, or we could try to solve for y. Here's a whole bunch of analysis they do. Let's look and see what they do with it. I mean, technically, the first thing we did just by substitution satisfies what they wanted, right? Right here, we just substituted in, done, right? But I have no idea what that is. Is that a circle, right? Is it a hyperbola? I don't know. Let's see what they do. So this is where we were, right? At one point, right here. Let's see if we move that over, square it out, and do some rearranging. So we have this, right? We have minus 3x squared. Uh, if we complete the square, that's what they did there, you could turn it into this. There we go. So we could see that it's kind of circle-ish, right? But there's a minus in here instead of a plus. So that's telling you that it's going to be a hyperbola, all right? And we get it where it's something that if you had this class, if you had this example later in the semester, you might be able to recognize that and go, oh, that's a hyperbola. I know what it looks like, okay? Y'all don't have that yet, so don't worry about it. They don't even show the graph of it here yet, but let's look at something else. I mean, the goal isn't to just mindlessly plug in the substitutions and that's it. You don't learn anything, right? Like I can look at this and go, r is x squared plus y squared, and sine is y over r. but r is the square root of x squared plus y squared. Done. And then we move on, right? We've learned absolutely nothing, right? So the goal here is to play with this stuff and see what we can do. If we multiply both sides of this by the square root of x squared plus y squared, we would get this, right? And if I moved the 2y over, right, I would get this. Here I could add, I don't know, I need some number here. I'm not going to go into detail, right? If I added some number there, then this would be x squared plus y minus some different number squared. Okay, so this would be a circle of square root of number, but shifted down if we graphed it, right? So this is like a circle somewhere, right? Which when you look at that, you might not think about it. It's like, how would you look at that and think circle? Well, let's think about graphing it real quick. It's nicely in the form of r is a function of theta. So let's pick an angle. An angle of 0. If I plug in 0 for theta, what is sine of 0? It's 0, right? So when theta is 0, r is 0. Boom. When theta is pi over 4, we get root 2 over 2. Root 2 over 2 times 2 is root 2. So at an angle of pi over 4, we have to go a distance out of root 2 over 2. Now at pi over 2, that's when sine is 1, right? An angle going straight up, sine is 1. So at this angle, we have 1 times 2. We'd have to go up 2, the distance 2. At 3 pi over 4, sine again is root 2 over 2 times 2 is root 2 again. So if you plug in different values for theta, you can see you're getting a circle up there is what you're getting, all right? All right, as theta goes from 0 to pi, right, sine is going from 0 up to 1 and down. So if you take the values 0 up to 1 and back down to 0 and be multiplying them by 2, basically you're getting a circle here. Oop, the circle of radius 1, right, but it's been moved up. So this would have to be a 1 here. So if we actually did the math, right, let's do the math here. This is 0. So if I added 1 to both sides, right, this is y minus 1 squared. Right, I should have just done the math, it wasn't that bad. All right, completing the square, I added 1 to both sides. So this is a circle of radius 1, right, it's the same thing as 1 squared, but it's been shifted up 1. But we want to be able to get to where we can look at that and be like, okay, yeah, that's a circle of radius 1 just as easily as we can look at this and say that's a circle of radius 1 that's been moved up. So here's the one where they have a double angle, okay? So first off, we got to get rid of this double angle. We would rewrite this as r. Remember, sine of 2 theta was 2 sine theta cosine theta. So use your trig identity first. Now if we do our substitution, r here is the square root of x squared plus y squared. Sine is y over r, cosine is x over r. So we have an r squared down here, so that's just x squared plus y squared. Okay, so we're done. Boom. That's the mindless part, just doing the substitution. But what does this look like, right? We could rearrange it, right? If we multiplied both sides by this, we would get what? X squared plus y squared to the 3 halves, right? This is 2, 2.5, wait, no, this is 1.5, yeah, 3 halves, 2xy. Kind of like, what are we going to do with this? see what they do with it. They don't give us a graph, but I mean, they rearrange things. Let's see, we got this far. I guess that's all they do. Doesn't really give us much insight though. But I mean, why bother doing this if you could just do this? I mean, I don't get any more insight out of this than I do that. But that's as far as I go in this example anyway. And that's it for this section. So basically all you have to do is your basic substitution. Now we're going to look at symmetries, okay? Symmetry. All right, remember that cosine was even, right? Remember the graph of cosine looked like this, right? So it was symmetric about the y-axis. You fold it over the y-axis, it matches, right? And sine was odd or anti-symmetric. All right, so what does that mean? Well, here's the graph of sine, right? So being anti-symmetric meant if you tried to flip over this, you would get this. You get the exact opposite, right? If you flip it over the y-axis, you get the negative of what's on the other side. That's what this means. Flip it over the y-axis, you get the negative of what's on the other side, right? It's upside down. You'd have to flip it twice, flip it down, and then flip it over for it to match. So this is anti-symmetry, this is symmetry, okay? So we want to look at the same thing in polar coordinates. Now, there's three different tests, all right? There's, what if you take both your coordinates and switch them to, to the negative version? What does that mean? If I make r negative and theta negative. Basically, if I have an equation and I switch r with minus r and I switch theta with negative theta and it gives me the exact same equation, like all those minus signs just fall out, then that would be a symmetry, all right? Well, what does this mean? Remember, this is your theta equals 0, and then here's r equals 0. So symmetry is going to be weird here, but let's say I have a point. Here's theta, here's r. If I switch theta to minus theta, I'm down here. Now if I switch r to minus r, I go up here. So this is minus r minus theta. So if you switch theta to minus theta, you're down here, and then if you switch r to minus r, you're up here. Ultimately, you're flipping over the y-axis. So switching r and theta to their negative is a flip over the y-axis. Okay, so in an equation, if you switch r theta with minus r minus theta, and the equation doesn't change because the minuses just all fall out, that means the graph is symmetric about the y-axis. So this is like your test number 1. Then we have like a test number 2. What are the other possibilities? Instead of doing both of them, let's just switch one of them. And then of course we're going to have a number 3 where instead of switching just theta, we'll just switch r. Right? There's 3 possibilities. Flip both of them, flip one, or flip the other. Each one of these gives us a different kind of symmetry. Yes. All right, I just picked a random point, right? If I make the angle negative, whatever that angle was, I'm down here, right? And from there, if I make the radius negative, I'm going in the opposite direction. That's what a negative radius means, right? It means go in the opposite direction. So from here to here is what happens if you change the angle to the negative version. Yeah, if I'd have done the radius first, I'd have been over here, and then flipped the angle, I'd have been up there. Yeah. All right. So let's look and see what symmetry this would be. So here's my little point, random point r theta. If I switch to negative theta, that just puts me down here, right? So test number 2, if you just switch out the angle with the negative of the angle, that's a symmetry about the x-axis. So this is y-axis symmetry. This would be x-axis symmetry, right? That means that whatever the graph is, if you flip it over the x-axis, it matches. They will call it polar symmetry because this is where theta equals 0, right? Because we call them the x and y axis. Well, we also have a r axis and a theta axis. It's different though. Like this is theta equals 0, that direction, right? The way y'all are looking at me. So they would call it reflection over the polar axis. It's weird though, because you'll see it right here. All right, what is the r axis? This over here is where the y-axis is where x is 0. The x-axis is where y is 0. What happens when r is 0? R is 0 means you're at the origin. So in polar, instead of having an axis, you have a point, right? It's the origin. That's basically like your r axis. That's you know. So we're going to see that this is going to be polar symmetry here. So if you go from here's r theta, right? R theta. If you go to minus r theta, basically you're flipping over the origin, all right? So that's another kind of symmetry. So you could see a circle has y-axis symmetry. If you flip it over the y-axis, it matches. It also has x-axis symmetry. If you flip it over the x-axis, it matches. And it also has, I forget what this is called, uh, the pole, symmetry over the pole. Pick a point, flip it over this guy, you're still on the circle, right? But a circle is the most symmetric object in the universe, right? So it makes sense it would have all the symmetries, okay? So these are the 3 different kinds of symmetry. Let's look at some examples so that this like sinks in. Um, and the reason why we want to do this is because we want to know what the graphs of these things look like. And so symmetry allows you to like you know it has y-axis symmetry and you know what it looks like on the right and you know what it looks like on the left. So here we have our 2 sine theta. If we do the test number 1, where we swap out both of them, right? Make the r negative, replace the theta with a negative. Well, sine is odd, so we can pull this minus sign out front. And from there, we can cancel both the minuses, and we end up with exactly what we started off with. So this guy has symmetry about the y-axis. We actually graphed this earlier. It looks like this. That's the graph. So yeah, it has symmetry about the y-axis. Okay. Here's a different example. Uh, so they're doing, this is test number 2. We're testing this, different equation, different example. We're testing it for symmetry about the x-axis, right? So if we replace just theta with a negative, cosine's even, so I could just throw that away. And I have exactly what I started off with. So this tells me that this thing is symmetry about the x-axis. And I'm going to guess what the graph looks like. I'm thinking it's probably uh, uh, something like that, or it might be over here. I don't know. But anyhow, it's symmetry about the x-axis. You flip it over the x-axis, it matches. All right. Here we're going to do the test number 3. So r theta goes to minus r theta. So we just replace r with a minus r. It's not the same, right? This has a minus on it, whereas this one doesn't. So that means it does not have symmetry about the pole or the origin. All right, so no symmetry. So just because this thing doesn't have symmetry about the origin doesn't mean that it doesn't have symmetry about the y-axis or x-axis. Like this guy up here, it's symmetric across this, but it's definitely not symmetric about the pole. If I pick this point, I'd need a point over here, right? If this thing looked like this, then this guy would have x-axis symmetry, y-axis symmetry, and symmetry about the pole. Because this point here would go to this point here, this point here would go to that point here, right? But we don't have that. We just have that. So we do have symmetry this way, not this way, and not over the pole. Okay, so you have to test for each one separately. Okay. Seems like if you'd have this though, symmetry about the pole, that you would automatically have the other two. Doesn't that make sense? All right, let's think about that. All right, like how could you have symmetry about the origin and not have both of these symmetries? Because any point here, you'd have to have a point there. A point here, you'd have to have a point there. I guess you could have something like this. Yeah, that's symmetric about the pole, right? Because a point here would go there, a point here would go here, a point there would go there. So that's symmetric about the origin, but it's not symmetric about the y-axis, and it's not symmetric about the x-axis. All right, so it is totally independent type of symmetry. Let's put that up here in our origin symmetry. Okay. Oh, here's their pictures here. Number 1, number 2, and number 3. Yeah. All right, so let's do our test. The number 1 test is replace both of them with their negatives. If we did that, we would get a negative r equals 2 sine of negative theta. This minus can come out. And then both those minuses can cancel. And this is the same thing we started off with. So we have symmetry about the y-axis. So that tells us whatever the graph looks like, it's symmetric about the y-axis. Okay. Let's look at test number 2, where we just replace theta with its negative. So I would have r equals 2 sine of negative theta. That minus can come out. So this is not the same as that because we have a minus over here. So no, we don't have symmetry about the x-axis. And let's look at the last one. If we just replace the r with its negative, we would have negative r equals 2 sine theta. That's not the same as this because this doesn't have a minus, so we don't have symmetry about the origin. If you look at the graph of sine, I think it has symmetry about the origin. Like if I take this point and flip it, I'm over here. If I took this point and flipped it about the origin over here. So anti-symmetry seems to be the same as symmetry about the origin. Because if you think about it, like if I had the minus sign coming out, so this is anti-symmetry is the same as symmetry about the origin when it comes to rectangular coordinates. And they call it anti-symmetry, but anti-symmetry has the word symmetry in it, right? All right, so here's the actual graph of this thing. All right, so you can see, boom, it's symmetric about the y-axis. It's not symmetric about this axis, and it's not symmetric about the pole. Okay? All right, so let's do test number 1. Replace both coordinates with their negatives. We would get minus r equals -2 cosine minus theta. Cosine's even, so you could just throw away this minus in there and then cancel out the minuses. So this is not what we started off with. There's a minus here, and we don't have one. So we don't have symmetry about the y-axis. We do our test number 2, where we just replace theta with its negative. That minus can go away because cosine is even. And we do have the same thing. So this dude is symmetric about the x-axis. You flip it over the x-axis, the graph is going to match. And number 3, just replace the r with its negative. We have negative r equals -2 cosine theta. The minuses would cancel. This is not the same as that because this one has a minus and this one doesn't. So we don't have symmetry about the origin. Okay. And the symmetry stuff is to help us with our graphing, right? Now, the other thing we want to do is find zeros and maxima, okay? Well, if you think about your XY coordinate system, right? You might have some kind of graph that you'd be like, oh, hey, this is important, and this is important, right? That's where y equals 0, right? Those were the zeros of the function, right? Well, with r and theta, this is different, right? Right, because this is y equals a function of x. We're setting it equal to 0, right? In our little like spherical world or polar world, right, we're writing r is a function of theta, right? So what would the zeros of these polar functions be? That's r, when r is 0. Where is r 0 at? Only at the origin. So when it comes to polar, right, with Cartesian, it's where the graph crosses the x-axis is of interest. In polar, it's where the graph crosses the origin. So instead of this whole line of interest, we just have this one point of interest where r equals 0. So there's lots of values of theta that could give us r equals 0. With an example. So r equals 2 sine theta. All right, so where is r equal to 0? Well, r is 0 anytime sine is 0. Right, here's my unit circle. Sine is the y value. So basically, r is 0, dang it, 0, when theta is any multiple of pi, right? And if we graph, we've already graphed this before. It looks like this. It's a circle, boop, boop, like that, right? So as you keep increasing the angle, basically you're going around the circle over and over and over and over again. So this graph, instead of like being this line that goes forever from the left to the right, right? We're taking that line and curling it up into a circle. So as theta increases, you just keep going around and around and around the circle, right? Instead of going infinitely far to the right, right? Like with X and Y, right? You let X get bigger and bigger and then Y changes, right? Here, as you let theta get bigger and bigger, you just keep going around and around in a circle, okay? So that's how you get the zeros. You just set this thing equal to 0 and solve for theta, right? When is sine theta equal to 0? Well, when theta is a multiple of pi k. We're also interested in maxima. Well, sine is always between -1 and 1, right? So the maxima would occur when is sine theta its maximum value, right? Well, unit circle says any angle that points upwards, right? That's when you would get the maximum. That's when this would be 1 and r would be 2. So the maximum value of r is 2, because that's when sine is 1, right? That tells you that this point right here is at r equals 2. Right? And the minimum occurs when sine is -1, right? Then we would get a -2. Maybe I drew this wrong. Let's look at the graph. So they just go from 0 to pi here. I drew it right. So this table, all they're doing is plugging in values of theta here into the equation, right? And figuring out what r is. Right? So they only did from 0 to pi. From 0 to pi gives you this. But I think if we keep going though, we should also get this down here. Like if we kept going with this chart down to 2 pi, thinking we should be getting the bottom half here, right? Because if you keep going, sine is negative, and then we would get a negative r value. Yeah, I think we should get another circle down here. Oh, they don't draw it there. I don't know. I mean, that's what you get if you. Let's see what would happen if we kept going. What about like 2 pi would be the same thing as 0. So what about 3 pi over 2? 3 pi over 2. We would have r equals 2 sine of 3 pi over 2. Sine of 3 pi over 2, that's a -1. We would get a -2, right? So yeah, if we kept going, we would get another circle down there. So we should have symmetry about both axes here. Let's check this thing out. If I replace both of them with negatives, the minus would come out and cancel. So that tells me I have symmetry about this axis. But if I just replace theta with the negative, that would come out, and so we shouldn't have symmetry about this axis. But it looks to me like we would if we just kept going with our angle here. I have to investigate that. Right? Because they keep drawing just this circle up here, but if you keep going, right, sine is negative from pi to 2 pi. Yeah, I'm sure you can. You just have to change the mode to polar. All right, so it knows what you're talking about. Okay. Hmm. Let's do another example. Huh? Oh, we're out of time, aren't we? All right, I'm going to ask the coordinators why they stop at pi, because if you keep going, you get another circle down here, which would imply symmetry about the x-axis, but they just taught us that you don't have symmetry about the x-axis. So I have a question for the boss. Right? All right, let's get out of here, folks.